So here we are trying to find the absolute extrema for the given function and justify our answer. So this is the same problem we had on a closed interval in a previous example. Here is the derivative. If I set this derivative equal to 0, I have a critical value at x equals 1, and it's the same critical value even on this open interval. So if I check anything less than 1, we get a positive number. Increasing any number greater than 1, we get a negative number. Decreasing. So then we have a local max on this open interval. Now keep in mind, normally we check in behavior with limits here to see what's happening, to see if there is an absolute extrema. But this becomes too tedious with the limit of this problem. So theorem 4.4.4 is helpful, and it's on page 271 of your book. It states if f of x is continuous and has exactly one relative extrema at x equals 0, or at x naught, then f of x naught is an absolute extrema. So think of this instance, right? It's continuous everywhere, but it only has one relative extrema, so it only has one point where it rises and then turns. So that one, this has to be the general shape of this continuous function. So this has to be the absolute max, and it goes down towards infinity, or negative infinity both ways here. So since f of x is continuous for all x and only has one relative max at x equals 1, by theorem 4.4.4, f of x has an absolute max at f of 1, which is negative 2. So this is, you don't necessarily have to remember the theorem number, but more the idea of if it has only one relative extrema on a continuous function, then that has to be the absolute extrema. So we'll practice this more in class.